Hey everyone, this is Ian. I am making this video to talk about battery pack basics. And the background is I was a chemical engineer by training and I understood a lot of things about electrochemistry and galvanic potential and stuff like that, but I never really understood how do cells themselves interact with modules and how do modules interact with pack and how does a pack interact with a vehicle. So that all of that is in the domain of systems engineering, which is what I am now. I'm a battery pack systems engineer. So I wanted to basically go over this to educate anybody who might have questions about battery pack design and stuff. And I made this image right here, which is showing a very simplified view of a pack design. But what you'll see there is number one, which is a giant loop where all the electrochemical energy is stored. It's stored in some configuration of series and parallel of cells. And if you have more cell groups that are in series, you're going to add the voltage of those cells. And if you have more cells that are in parallel, you'll add together the capacity of those cells. And then from the ends of that, you're going to get like it's going to have some sort of distribution that goes towards a positive gate and a negative gate. And then these are called your positive and negative contactors. And the way you can think about them is they're literally gates. They open and shut. When they're open, no energy passes through them. No, I mean, no energy is supposed to pass through them. Everything after them is not at high voltage. But when they close, everything after them now is at high voltage. Everything pre-contactor and post-contactor is at high voltage when they're closed. So this is what basically delivers energy out of the pack towards the drive units, enabling you to drive the vehicle. And then number three is where there's a little bit of nuances because companies are usually doing it differently, but there will be a high voltage and a low voltage distribution system after the contactor gates, which are carrying high voltage out of the pack or maybe bringing in low voltage into the pack. And the way I can best describe it is you can see here lead acid battery that I wrote here is delivering 12 volts to the contactors, enabling them to open and close successfully. And then also you can see a little bit of red wiring like after the contactors. That's basically enabling high voltage to go to the drive units. But there will be like some sort of bus bar configuration or some sort of like wiring that takes the high voltage and enables it to exit the pack through some headers of some sort towards the drive unit. So basically, to summarize, the three parts of battery pack is pre-contactor, your contactors, and then post-contactors. And I also have some calculations here for anyone who's interested. I have 4 cells that are in parallel, and then I have 5 groups of cells, so 5 series. So this pack right here would be considered 5S4P, 20 cells total. The theoretical capacity of this pack is 4 cells in parallel, so it would be like assuming a cell is 4 amp hours, this pack would be 16 amp hour capacity. And then because when you add things in series, it adds their voltage together. If you assume the nominal voltage of a single cell is 3.65 volts, and there's 5 groups in series, so the total pack would be 18.25 volts. And then the theoretical energy of the pack, which is calculated in watt hours, would be 16 amp hours times 18.25 volts is about 292 watt hours. So this is just like an example of some very basic calculations, but there are many different system calculations that inform how you design a pack for a specific purpose. So if the requirements are flowing down from the customer or from leadership, it's like we need to build a vehicle that has like super fast 0 to 60 time, then you might want to consider something that has very high voltage, right? So you maybe be putting more things in series. Whereas if leadership is telling you like, oh, we want to make like a very low cost, high range vehicle, now you got to start thinking about, oh, we need to have more things in parallel because we want to increase our capacity more. So just for reference I have here, the Hummer EV pack is more than 200 kilowatt hours. It's actually 2 packs that are stacked on top of each other. That's what's on the Hummer EV. The R1T large pack is 135 kilowatt hours, and the Model S pack is it's like around 100 kilowatt hours or something. So this 0.292 kilowatt hour example pack that I made here is actually a really small. So usually you're going to have many more cells than this. So this is just a very simplified model. In this next slide here, I have battery pack basics specifically for the cell. This is where kind of I have my forte as a chemical engineering major. But I explain here that the building block of a battery pack is the lithium-ion battery cell. Usually we're just calling this a cell, and there are many companies that are building different kinds of cells, but right now everyone is using lithium-ion pretty much. And the cell is the basic building block that holds electrochemical energy at the top of charge, which is referred to as 100% state of charge or 100% SOC. The voltage from the positive to negative end of the cell will be 4.2 volts. Typically it's 4.2 volts. And at the bottom of charge, which is 0% SOC, the voltage from positive to negative end of the cell will be around 2.5 volts usually. And the reason why you don't want to go outside of these limits, 0 or 100, you could, but the reason why you don't want to is because when you go over 4.2 volts, now you're over potentialing the cell. And the reason why that's an issue is because basically how the cell works is there's cathode, anode, a separator in between, and then everything's submerged in electrolyte. And on the outer edges is current collector. It's like where the current is being transferred around. But if you take the cell over 4.2 volts, let's say 4.4 or something like that, you're basically shoving ions towards the anode at a very high potential. And what you're doing is you're basically like intuitively you're pressing the ions into the anode faster than the ions can intercalate into the graphite. They can't disperse into the anode fast enough, so they build up on the edge, and then you're going to get lithium plating, which is lithium ions building up on the anode. Over time, when you plate enough lithium, it'll form like little dendrites. And remember how we said it's cathode, separator, and anode? The anode dendrites will actually go through the separator, touch the cathode, and then short out your cell, and then your cell will be dead. So that's why you don't want to go over. And if you go under voltage too many times, what will happen is the current collectors, which are on the edges of the cell, past the cathode and anode, actually the copper will deionize, and then it'll turn into ions, or sorry, the copper will ionize, turn into ions, and then the copper will actually form dendrites that will short the cell. So you don't really want to stray outside of these normal limits, which is considered the normal safety limits. And then now I have pictures of 3 different kinds of commonly found cells. The first one I want to go over is the top left one, which is the cylindrical cell. It's used in a lot of vehicles. And the cylindrical cell, it's a jelly roll, so it's cathode, anode, separator in between, and then current collectors on the outer edges, and then it's rolled up into a can. It's usually holding a lot less capacity than a pouch cell or a prismatic cell, which we'll go over next. But the interesting thing is the entire can, the entire surface, edge surface and bottom surface, is usually considered the negative tab. And then the button on top, the little space on top, that little circle is considered the positive tab. And then the other type of cell that's commonly used is pouch cell. GM is using this kind of cell, with working with LG to build this kind of cell, and it's very simple. It's actually, instead of the metal can that the cylindrical cell is using, usually pouch cells are encased in some sort of flexible plastic material like polypropylene or something like that, and then you have metal tabs that are coming out the edge, and then those are your positive and negative tabs. Super simple. If you want to connect them, you just weld them together. And then the last one that's getting more common these days is China is making a lot of these, is prismatic cells in the top right. Prismatic cells is just like a rectangular prism or a cube or something like that. And then it's a hard case, it's prismatic shaped, and then there are 2 terminals coming up the top, a positive and negative end. So I have a little bit of electrical basics here with battery cells. You put cells in series by connecting butt to head and butt to head and butt to head and so on. And I apologize for calling it butt to head, but that's just the colloquial way that I like to call it. It's just negative to positive, negative to positive, negative to positive. So actually in this image here, you can see that the negative most is on the left side and the positive most is on the right side. But you can see that every single positive end is connected to a negative end in this configuration of 12 cells. So actually this configuration of cells would be called 12S1P because it's 12 cells in series. Cells in series add their voltages together, and cells in parallel add their capacities together. And then on the bottom image, you have cells that are in parallel. You connect things in parallel by connecting butts to butts and heads to heads. negatives to negatives and positives to positives. So at the bottom, you can actually see that um, it's a group of 3 cells in parallel, and there's 4 groups of them. And the way you can tell they're in parallel is because there are 3 welds that are coming off, 3 tabs that are coming off of each group of cells, and then they're being connected together. That's all the positives touching each other. And then there are 2 tabs coming off of each group of cells that are touching the negatives together, the 3 negative cans together, and they're connected. And then you can see that the positives are connected to the negatives, and the negatives are connected to the positives, and so on. So that is a 4S 3P configuration, just for a quick example. So like for example, you could have a circuit that's 100 series group, 100 series groups of one 4.2 volt 4 amp hour cell, and then the voltage of your circuit will be literally just 100 times 4.2, 420 volts, but the capacity would only be 4 amp hours of that circuit because they're all connected in series. Or you can have a circuit that's 10 series groups of 10 4.2 volt 4 amp hour cells in parallel. So you still have 100 cells, but now the voltage of your circuit is only 42 volts because it's 10 series times 4.2 volts. But the capacity would be 4 amp hours times 10 cells in parallel, so it would be 40 amp hours. So this leads to certain systems design choices, which I may discuss in later videos.